together. So let's consider this feedback system. I have a reference R here, R of S, and here it's my summation block. So I have negative feedback. Here is my system. Let me call it G of S, and here is my output. I will call it C of S. And in my feedback is not unity feedback. I have a sensor dynamic which I called H of S. So your exercise is you need to convert it to an equivalent unity feedback system. Convert it to unity feedback system. So here you don't have unity feedback. You need to convert it to a system where you have here unity feedback. So you need to do block diagram reduction and so on. Conversion, if you wish. Block diagram conversion. So this is, you will get a solution converted to unity feedback system. Okay, that's the question. Solution because we always when we studied system types almost based on a unity feedback system. So what if my system is not unity feedback in that form? So then this is its equivalent to G1 of S. Alright, here C of S, and here is minus, so plus and minus, where G1 of S equal to G over 1 plus, if you wish, G of S, H of S minus 1. Okay, so then these two systems are equivalent. If you don't believe me, you can verify it. How to verify it? How you can verify that those two systems are equivalent? Students?
Doctor, we do the loop forward over 1 plus loop. We should obtain the same result.
Very nice. So you do C over R for system 1 and see if it is equal to C over R for system 2, if that's system 2. Okay, this exercise 1. Let's do another exercise.
بس دكتور نجد minus 1 بالجي of S H of S.
This minus 1?
Yes.
But this I'm telling you G1 equal to that. G1 equal to that. So I replaced G1.
Okay. G1. Okay.
G1 equal to G over 1 plus GH minus 1. So I like to write it without S because I like this way.
To هاي minus 1 منين جبته؟
Yeah, this minus 1 you need to that's how to convert system 1 to system 2.
انت مش انت حطيتها forward على 1 minus loop or 1 plus loop.
If you are not sure, you are not sure about the solution, you verify it by looking to, as Tariq said, C over R for situation 1 and situation 2, and you need to find they have same closed loop transfer function. Considering that
Can I for
دكتور بس في لك انا 1 dot ولا لا؟
Yes, go ahead.
دكتور احنا مش رح نعرفها هي forward على 1 plus loop مظبوط؟
Yes.
اوكي. فإذا هون ناخدها هيك فهي بصير G of S على 1 plus G of S H of S.
Yes,
مظبوط.
this is C over R. But here
Yes.
I'm not finding Z of R. This is G1. Maybe G1 equal to, I'm saying your G1 is equal to G1 plus GH minus 1.
اوكي
This is
صار.
G1. G1,
ماشي.
not the closed loop. Closed loop transfer function you need to find yourself. So you find the
اه
closed loop transfer function for system 1 and you find the closed loop transfer function for system 2 and check that they are equivalent. So what
اوكي
I'm
دكتور.
saying to you, I'm saying like system 1 is equivalent to system 2, taking G1 equal to G over 1 plus G H minus 1. If you take G1 equal to G1 plus GH minus 1, you will find up like system 1 and system 2 are equivalent. How to verify they are equivalent? So you can find the closed loop transfer function for both systems. Any other question regarding exercise 1? Is it clear? So from now
هي
onward,
كلير دكتور. بس
yeah,
هاي الجي 1 يعني ناخذها انه فورمولا اللي بدنا نحولها ليونتي كان نستخدم هاي الفورمولا انه هيدا الفانكشن الجي 1 ايكوال جي على 1 بلس
very good, Muhammad.
جي.
Yes, exactly that. So this you can take it as a general rule now. If you have a system and you want to convert it to unity feedback, in case you need to use it somewhere to find system types and so on, it's very useful. You use this form. Exercise 2. So exercise 2. Where is my exercise 2? Give me a minute. This is my exercise 2. Okay. We saw in class the derivative feedback rate. So proportional plus derivative feedback, or what we call it derivative rate or derivative velocity. And we said it is what? First, let me take this block diagram for classic PD controller, proportional derivative controller. So minus, that's the classical KP, I know, plus KDS. This is a classical PD controller. And assuming my system is a moment of inertia of a rotating shaft, J is moment of inertia of a rotating mechanical system. So JS plus 1 over S. So yeah, assuming this is the dynamic of a rotating shaft system. Also, it is plus P. Let's assuming you have on your shaft, you have bearing on your shaft that's rotating. So that's the system. Also, it's similar to a DC motor position control as well. You remember it was A over TS plus 1 over S. Somehow it's similar system also. Also, we are doing position control here. We are doing position control for the angular position of the shaft or the angular position of the DC motor. So it's same, but this is not the point now. That's my C of S. I name it C of S, and here is my feedback, unity feedback system. That's a classic PD controller. For a system like that, I know I don't need integral term, especially if my input is step. So most probably I need to damp the overshoot and so on. So we use basically PD controller. Okay, but we said we have a different way to do it, is using proportional plus velocity feedback, or yes, if you find the transfer function of this one, C over R, which we done in the lecture, we found like equal to Kp plus KDS over GS square plus B plus K DS plus KP. This in our previous session when we was demonstrating something similar, we find our transfer function and we said this has 0 and 0 is not desirable effect. So that's why it's recommended to do proportional plus velocity feedback. So what we did, KP, if you remember, we keep the KP here. So we do proportional control for the error and we feed back directly the output to the derivative system. Alright, so and what we did, this is my plant 1 over GS plus B 1 over or S. This is my plant and this is your C of S, and you remember what we did is 1 plus K, who will help me, KD over KPS, you remember, and that's what we called proportional plus velocity feedback. And if you remember, when we computed C over R for this system, what did we find? We find a similar same poles but without 0. So we found C over R equal to KP over GS square, same poles, same characteristic equation, B plus KDS plus KP. So you see both system. So here is with 0, here is without 0. I hope you remember them, right? Do you still remember them from our part 2 here, which you have it on Moodle? You saw them? You remember them now?
Yes, Doctor.
Right? So those are the two systems we found. This we call it proportional PD controller versus we did P controller plus velocity feedback. Why velocity feedback? Well, if you wish, we have here because here you have the derivative term is here. Also, if you wish, we are feeding back. If this is a position, then we do derivative for your position. It becomes velocity. So we're feeding the velocity. Okay, so now the question, what is the exercise here? Still didn't ask any exercise. So demonstrate that this is number 2 if you wish, or system number 2. Okay, if this is system 1 and this is system 2, so the equation is demonstrate that system number 2 is equivalent to the following system number 3, which is R of S plus minus KP, alright, then 1 over GS plus B S, okay, C of S minus plus in here, what do I have? I have KDS. So I'm feeding back the velocity I'm feeding back the velocity, because this is position, angular position. I do the derivative, I'm feeding back the velocity, and also I'm doing proportional control for the error. So I'm multiplying the error by a proportional constant. It's coming here, and then so here is what we call it proportional plus velocity feedback. Feedback. I'm feeding back the velocity. So if this is position, the output is the derivative gonna be velocity, or rate if you wish, rate feedback we call it sometimes. So demonstrate that 2 and 3 are equivalent. So that's the question. Demonstrate that 2 and 3 are equivalent. Demonstrate that 2 equivalent to 3. So yeah, how we go?
Block diagram, doctor.
So
We minimize them to find C of S over R of S.
C of S, so you want to find the closed loop transfer function for 2 and check if it is equal to the closed loop transfer function of system 3, right?
Yes.
Okay, excellent. That's it, as simple as that. That's what you want to do. So then the solution is you need to check that C over R for system 2 equal to C over R for system 3, and you find they are the same. So now I want you to remember that they are the same. Okay, so then remember it, and you will have ending up having C over R equal to KPG S square plus B. So you will do the derivation at home. So any question regarding this exercise? Yes, students? Any question?
دكتور نحن المفروض نعرف انه position plus velocity feedback looks like this.
Yes, it's a good practice to know it, because at the end you are eliminating the effect of zero. If you are doing this classical way, usually we try to avoid it. We try always to avoid the effect of zero. So we do it, we usually do in practice, we do proportional plus velocity feedback instead of doing PD control. We do P plus velocity feedback, proportional control plus velocity feedback. This in practice we do because we eliminate the effect of zero, which is unwanted.
دكتور بس ما هو الزيرو مش بيعمل system faster.
But usually yes, but you can make the system faster by the proportional term as well, or also the derivative term make the system a little bit faster.
دكتور adding a derivative term مثل كأنك عندك زيرو صح؟
Yeah, and the derivative term in the denominator, also when you switch them, when you design them, you can design them in a way having Kp and Kd that give you a fast system. Your desire, it will give you the desired system, because here you have two parameters you can play to position your points, Kp and Kd, to fit your desired location. So you can choose the desired location, but with the advantage that you don't have the negative effect of zero. If you remember, to reach your desired point you need to go back, then later on go up. So then you eliminate this negative effect of zero. Alright, so from now onward, this is the proportional velocity feedback control that we recommend to you. A side note, and it's an important note, that I don't want you to forget always that this is not how we put in practice our derivative control. So usually in practice our derivative controller KDS if you wish, KDS. We don't put it this way. So if this is position, assuming this is my position, I'll call it U, it's alright, and here I'll call the velocity as Y. We don't put it like that in practice. In practice, we put N over S plus N. What is this S plus N over S plus N? Could you remind me?
filter.
It's a low pass filter. First order low pass filter. First order low pass filter. And this is needed to filter the noise, but also to make the system physically realizable, because you don't have system where the denominator more than the degree of the numerator more than the degree of the denominator. So in this way you have equal degrees of physically realizable system. Also it has the advantage of filtering the noise. That's the in real practice system. And it's the frequency, the cut-off frequency. So sometimes you see maybe omega f if you wish over S plus omega f, but the same, it's the same. Okay, just I'm giving a different sample. And that's your KD if you wish. All right. This system is equivalent, so I continue my note. This system is equivalent to, or let me take this system, just those are the same anyway, these are the same, but I'll take the letter N because I like the letter N. So this system is equivalent to my U, my KD, or you may find it in some books they write it D, simply D, or instead of KP they write simply P, is alright. So KD plus minus N Y 1 over S. Do you agree that those are equivalent? So system 1 and system 2 are equivalent. Let's do the closed loop here. What's the closed loop here? U KD, and then could you help me find the closed loop here? Yeah, who will help me? Yeah.
Yes, doctor.
Yes, go ahead.
Yeah, n over n plus 1 over under 1 over s
So forward over 1 plus loop.
plus n times 1 over s.
Thank you, Saad. Thank you, Saad. So then this is my system. So is it 2 equivalent to 1? Able to see it? Not yet.
Yes, yes, doctor. Equivalent.
They are equivalent, right? Because if you take S common here,
نضرب دكتور بقاس ونقسم ونضرب فوق بقاس بيمشي الحل.
right? Okay, then you can see it. So look to, if you go to your MATLAB, this remind me by the block diagram in MATLAB. If you look to your MATLAB and see how MATLAB are doing it, look to their function. Can you see it? It's n over 1 plus n times 1 over s times d or kd is alright. You can see the derivative term, so they add a filter. So this n is the cutoff frequency, filter coefficient if you wish. All right, is able to see it in your Simulink block? What is this n over
Yeah.
1 plus n 1 over s? Okay, good. So it's recommended to work it this way. This is note number 1. To continue on something, to continue also on note number 1, I want to say, Suzanne, why MATLAB? Just in your opinion, I'm not sure if you know, maybe you tell me you don't know, but just I'm wondering to ask you, especially those who take numerical analysis. Okay, if somebody take numerical analysis, if he able to answer this question with me. So this is system 1. Okay, I'll put it in green, and this is, if you wish, system 2. I'm putting it in green as well, and they are equivalent. So why MATLAB used this one? It's just the system we saw in MATLAB, n over 1 plus n 1 over s times d. Why MATLAB simply they didn't use n over s plus n times s d? Yeah, why MATLAB, for example, the block in MATLAB, you saw the block in MATLAB was d n over 1 plus n 1 over s. So why MATLAB didn't use d n s plus n times s, which is 1? Why MATLAB didn't use system 1? They used 2, but they are equivalent. Do you think there is any difference in between these two, or they are exactly the same?
دكتور هون الفانكشن بتغير هون، فهو بياخد بس الفانكشن 2.
Yeah, why he took 2? But they are the same. I am seeing them, they are the same. You just told me if I
حسب
multiply.
الديفرنشال ايكويشن تبعه.
Sorry?
حسب الديفرنشال ايكويشن تبعه.
But you told me if I multiply by s here and there, 1 and 2 are the same. So why MATLAB? MATLAB could use simply this one. They are the same, right? So here I'll tell you, actually yes, they are the same, but if you want one is easy to read and understand. If you look at it, easy to read and understand. You have derivative term ds times filter. Easy to read and understand. Directly I can say, okay, this is derivative term proportional constant, derivative constant of proportionality times the derivative s and my filter. So easy to read and understand, but more math operation and memory to accomplish. This is need, if you go in numerical analysis, you'll find this is need more computation power. So need more memory and more math operation to accomplish the derivative. However, the second one is more computationally efficient algorithm. So the algorithm, if you do numerical analysis for this one to get the result, so it's more computationally efficient. It's more efficient in that sense. That's why MATLAB try to optimize. And just a side note, okay, that's why MATLAB use this one, but it's easily you could use this. Both are the same. Okay, we end up our notes. Any question regarding those exercises we did? Yeah,
No,
no question.
no, no. واضح.
All right, so
اعتقد كمان انه الماتلاب بيستخدم 201 عشان يخفف الرام، شغل الرام على الكمبيوتر، صح؟
yeah, it's more computationally efficient. So like RAM, but also math operation is less, time consuming is less, so it will take less time to solve it. PID
تمام،
control.
واضحة واضحة.
So last time we did more, we focused more on on-off control, which you saw it before, but I wanted to show it to you again. Now we'll go to PID control, but I will go very quickly. because we also saw them, but just I want maybe to recap some idea, and I'll share the slide with you. There are many errors in the slide, few errors in the slide, but I'm not correcting them. I'm keeping them with errors because it's better to keep errors. So this is the PID control block diagram, which you know. Position control. So I'm seeing me. I'm moving faster. You will have the slide. You'll be having the slide, like the application of speed control, for example, and why PID is used. Easy to design and implement. Industry standard, solves 90% of the control problems. So this we know: output, control signal, disturbance, noise, sensor noise. Okay, reference or set point. That's a plan, that's a controller. Okay, you could do proportional control, etc. And this is a proportional control, of course, in Laplace domain and in time domain. Effect of proportional, you can look at the effect of proportional. Peak time decrease. So like the peak time decrease, it's here rather than here when you increase the proportional, but also make the system faster, for example. But you have overshoot. Okay. Here we represented this last time when we was talking about on-off control. This is a pump, water tank level, and you want to do proportional control for it. This is a pump voltage that takes. So the dynamic of pump is included in, assuming it's included in the tank itself. But here you add it to tell like minimum voltage it can take is 0, maximum is 22 volt. And I wish I'm still opening it somewhere. Alright, maybe I go to the library, and if I go to the discontinuity, maybe double click. So here we have this saturation block that we saw in off control. This you could use it here between 0 and, not necessary to be as they are saying here like it's symmetric. No, you can put the minimum is 0, the maximum is 22, lower limit is 0, upper limit is 22 volt. Okay, so that's how you model it. You model your saturation block, so it doesn't accept any value below 0 and doesn't cut off any value after above 22 volt. Okay, then you do proportional controller, you look to the signal and so on. Here is proportional control for a servo motor. Okay, that's the position servo. Why it's servo? Because it's DC plus position control becomes a servo. Call it control of servo, because you are controlling the angle. So then it is your DC motor, but you are doing the position control. Okay, the motor take between -5 and 5 volt, this particular motor, assume. So it moves in the forward and backward direction. This is your saturation block here, so -5 to 5, so it's symmetric. And this is the famous plant of a position control of a DC motor. You can look at it, seeing drawback and benefit of proportional. So you'll go over the slide. All of this we explained, but you'll go over the slide. You see different presentation style if you wish. You go over them yourself at home because we already explained. So PD control same. Also this we saw before. So parameterized PID equation commonly used in industry. So if you don't want to use KP plus KDS as this, how use it this way. K common, so instead of using it this way, you can use it this way, and we already saw it before. Take K common, and this we call it parameterized PID equation. Parameterized, where K is the proportional, TD is the derivative time. Okay, so we saw it in previous sessions. Just so here what they did, they fixed KD and they fixed KP at 10 and they start increasing KD to see the effect of KD. But you may find here some error. Okay, so you will look at them in their notice. So you will look because we already did them. So don't take them as granted. For you and for me, usually for everybody, everything is wrong until you prove it's right. And this is a rule I learned from my old supervisor. Everything for you is wrong until you prove it's right. So don't take anything as granted. Okay. So in these slides, you may find some errors in your conclusion, but I don't want to go over it because the fundamental of we already explained before. Okay, this is PD, but if there is something really clear, I may point it out. But otherwise, here you need to figure out what do you unitize and see. Maybe sometimes it's decrease, they put increase or so on. I don't remember where it is exactly, but yes. So, but our previous slides that I gave to you are all correct. But in here, so I want you to reflect on and think on what you are really analyze, and this is a good point to learn from. Okay. This CPD are comparing usually, and this is a good practice, always look to the motor voltage V. That's the motor voltage V, VM here, or U, which is the output of your control. Okay, as you see, maybe as we saw in even before in this example, maybe I didn't mention that's the motor voltage. Okay, they looked at U. They didn't look at U. This schematic is not U, is the V. VM like voltage of the motor, M like a motor. The voltage of the motor, which is above, is after the saturation block. Okay, it's good practice to look at it to see if your system is saturated or not. So it's not saturated, it doesn't reach 5 volts, for example. Okay, so at the end I'm visualizing the control signal, because the control signal and the voltage motor are the same because there is no saturation. So it's good practice to look to the control signal in addition to your reference and how you are tracking your output. Alright, so as they are doing here. Okay, so then when this is a proportional control they did before for that system. So then when they added PD on it, they find there is no overshoot, which is a good point. So here with P, but with PD there is no overshoot, but it's saturating the actuator a bit. The actuator saturates at 5 volts, so you can see we are reaching the 5 volts at the transition point between at 1 second when I want from 0 radium to 1 radium angle. So then it follows it without overshoot, but I'm saturating my actuator a bit. Okay, so what about noise? Here is a clear wrong thing. Just maybe we said this is omega f or n is alright, right? So according to what we said is omega f or n. Remember we said D, we have D or KD, then you could have N, we said N 1 plus N 1 over S, or omega F if you wish. So omega F, this KD, omega F 1 plus omega F, so this is 1 over S. Okay, so according to this analogy we did before, so this is omega F, or we said this N is omega F, same, is cut-off frequency of your filter. So here is 1 over S. Okay, just they forgot to have it this way, but anyway, so you pay attention to. At the end they added a filter, so here just to know that they added a filter, and they need to see the effect of noise on the system. So they added noise as well, and they are looking to the effect of noise with and without filter. Okay, PD control with no filtering. Here is the PD control with no filtering. I having noise, so I have noise, but I have no filter. I have simple PD control. So if you look to the position at 1 second, it's noisy. The measurements are noisy. So that's the actual servo angle. It is noisy, whatever I'm measuring from my sensor, and that's my desired. So I'm following it, but with noise. Servo response tracks desired servo angle well, but there is a noise. Remember when we had no noise, it was overshoot. It went without overshoot, but it was saturating. But here when I added noise, control effort voltage going to servo is noisy. Okay, that's the control effort. That's the voltage that's going to the servo also is noisy. Okay. What happens when I add a filter? Still noisy, but not as much. Adding filter lowers noise, but it doesn't eliminate it. So it lowers your noise if you wish. So if you look at the noise here, for example, it's more clear compared to here with no filter, here with filter. So I'm filtering the noise, so lowering noise, but it adds overshoot. So look to your system now. When I added filtering, so this adds, that's the effect of filter if you wish. Control effort going to servo is more smoother now. It's not as noisy as with filter. Okay, you look to the takeaway, maybe in the takeaway some increase instead of decrease, I remember something. So PI controller, it is, we know, they fixed KP and they keep increasing KI and look to the things. Maybe here there is something wrong in the conclusion, but doesn't matter. You will analyze it yourself. So they go to the pump level control, they did PI controller on it. That's the proportional, so there is no tracking and there is saturation. So it's saturated at 22. So here like I have 22. It looks like it's saturated, and there is no tracking. You have steady state error. So that's the actual water level, which is 10, but your desired was most probably like something 11 or so between 10 and 12, maybe 11 centimeter your water level, but you get something like 10. So you have one centimeter error with the proportion. It doesn't track desired water value level. So the voltage going to the pump is smooth, but there is saturation. Okay, what if I add PI control response? So here it's not recalled, it is a PI control response. We saw it for the first time. Tank response track desired water level. So you can, if you want, take out recall. The tank response tracks desired water level well, but large overshoot. So it leads to some overshoot. So it leads to instability. If you remember, compared to derivative term, it give you all, it improve, it dampens the overshoot. But this, it will amplify the overshoot. It may lead to instability at the end, if you wish, the integral term. But it has the advantage of eliminating the steady state error. Control if voltage going to the pump is smooth but saturates actuator. Well, here also saturates the actuator, but it tends like it's saturated more. You see, like here it's still saturating up to 2 seconds, but here it keeps saturating up to around 4 seconds. So it saturates the actuator more. So your control effort you are spending is higher when you're adding the integral term. So your control signals, so the voltage sent to the motor is higher. Your actuator here in this case is a pump. Okay. PID controller, which we know. Alright, this is the parameterized PID equation. You take K common 1 over Ti, Td. Ti and Td are the integral and derivative time respectively. Okay, as we know, present, past, and future. So we take PID for servo position. So this is I'm moving fast, but you can stop me in case something you feel really you are still missing it. But I'm assuming we are recapping here, more as a recap, just to fix the idea and revisit some important ideas again and again. That's it. PID. So you please feel free to stop me in case something you feel you still need to know about and you don't master it. Okay, in here, PID for servo motor position control. So that's the servo plant or the position control of your DC motor, A over TS plus 1 times 1 over S. So you have the motor limits. It takes in this motor that they have on their the motor they have on their system, it's between -5 and 5 volt. Maybe your motor more likely to be, for example, -12 to 12 or -7 to 7, not sure. So then here the motor limit, it takes -5, the maximum rotation in the reverse direction and the maximum rotation speed in the positive direction. I added here a friction, or they added a friction here to the system. To actually, why we want to add friction, and why you think this is added actually? Why do they need to add? Is there any reason? What it represents, or the correct question I could ask, what it represent? This friction block they added. What did it represent? Yes, students?
Load.
Yeah, it represent disturbance. Okay,
I said load, doctor.
okay. So one said disturbance, and one said it's a load. Yeah, any other two? What do you think could be this friction? Is this friction on the motor itself? You know, experimentally, so mechatronic students maybe can help. Uh, Experimentally, is there any small voltage can turn on your motor? Because we know the rotation speed is proportional to the voltage you are applying. So it's proportional to the voltage you are applying, right? Proportional. But is there any voltage can turn on your motor, or actually there is a threshold in which your motor start running? Do you think any small voltage you apply to your motor will start running, or there is a threshold?
في threshold على ما اتذكر هيك بتوقع.
Yeah, thanks Muhammad. So where is the mechatronics student? Are you absent? Are you with us in class? Mechatronics student, did you experiment before a DC motor? Do I have mechatronics student in my class?
ايه اكيد دكتور اكيد.
Yeah, so you know, when you apply voltage to your DC motor, it doesn't directly turn on. It needs some minimum threshold voltage in which your motor will start rotating. And this is because of the so Tariq said load, and he's right. This is because of the load of the disk itself. So you have the load of the disk itself on your shaft, on your motor, or the weight of the shaft and the disk rotate. Is you have this inertia of your shaft, of your disk that's rotating. So to overcome this mass, to overcome this load, which is internal load, it's kind of friction, if you wish. So that's how we, if you wish, that's how we simulate it in MATLAB, by this friction. And a friction, I showed it to you last time here. It's Coulomb and viscous friction, which you could put it. Okay. Or yeah, it's more likely you have this dead zone actually, rather than this friction friction one. So this is different little bit. So this is dead zone actually. but you could use friction in if you are simulating friction. Here it's a dead zone. Okay, and for on off usually we use relay, but we are not interested in. Any question? So here is response with proportional controller for the system. That's a proportional controller. Overshoot, steady state error. PD controller, no overshoot, reduce the overshoot, still steady state error, but saturating the actuator. So you eliminate this overshoot, but it's saturating the actuator. What's the cost of saturating your actuator? Then adding integral now. What happens when I add integral? It eliminate the steady state error.
Steady state error.
Right, that's the important. And still the actuator saturating. So that's the effect of.
Doctor,
Yes.
how do we not saturate the actuator?
But you need, it's a trade-off. If you don't need to saturate the actuator and you need to track well, maybe you need to slower the system a bit. So then you tune your parameter. In the case you slower the system, you don't go fast as this. Maybe you allow some more overshoot in your system. So then if you want as much as you want a perfect tracking, as much as you will need to provide more voltage, more control effort to your actuator to react faster. Good. So it depends on you. Do you want, if you want, you don't want to consume your actuator, then maybe you need to don't have a lot of constraint on your desired response. Don't say I want a perfect desired response, perfectly tuning very fast with no overshoot and with steady state error equal 0. No. So then you decide what you want to do. Maybe you decide to change the actuator at the end, but this is more costly solution, and you need to change the system. Okay. So now we talk about design. So this is also something we saw. Usually in design we do pole placement control design. We do system identification between our desired closed loop transfer function and our actual closed loop transfer function, or if you want, between your desired closed loop characteristic equation and the actual characteristic equation, which includes Kp, Ki, and Kd. Or if you wish, between your desired pole, closed loop transfer pole, and your closed loop transfer pole. So you do this system identification, okay, to design your controller. So also it's a good point to take the attendance. Yes. So proportional control design. This is standard second order system. Omega n natural frequency, zeta is the damping ratio. That's a percent overshoot, which is, and this is the peak time. All right, that's the response, that's the reference. In blue is the reference. And yeah, effect on response. What's the effect on response of omega n, which is the natural frequency? Natural frequency affects the response speed. Let's say natural frequency affects the response speed. If you increase the natural frequency, your system becomes faster. This in time domain. In frequency domain, you can see it better. So omega n, it reflects the speed of the system, how fast your system is. If you keep increasing the natural frequency, you are increasing the speed of your response. So your response will be faster. So that's why it affects the response speed. As you can see, between 10 radian per second and 20 radian per second. So if I have the system like that and I apply step input, or okay, here they take step of 1.5, it doesn't matter, but you have zeta, you take a value of zeta and try to have two different value of omega n and look to the step response or a 1.5 response. Then yeah, so you get two different values. So then you conclude that omega n affects the speed, increase the speed. What's the effect of the damping ratio? Between 0.7 and 0.5, of course, it is like that. If I take 1, it's critically damped. Over 1, it is overdamped system. So we know how to compute the overshoot. A lot of students, they get confused, and this is, I found it's a good slide because they are taking when the step input is not unit, is not 1. So when the step input is not 1, because almost the student forgot to divide by the steady state response y. So because they assume y equal 1, so then they said percent overshoot is y max maximum minus the steady state times 100, and they forgot to divide by the steady state because they assume it is 1, but it's not always 1. So in this case it's 1.5, for example. So then y maximum minus, so y maximum it is 2 minus 1.5 over 1.5 times 100. So this is your percent overshoot. Will be 2 minus 1.5 over 1.5 times 100. Alright, so also we saw the percent overshoot 100 times if you wish, or if you don't want to, the 100 means it's not in percent. We know this formula, but also I recommend you to use the curve I was giving it to you, so it's much faster in your exam, so save time. Instead of doing the calculation, you use the curve. Okay, pi over omega d, this is omega d. So how to design proportional control of this system? I have a system like this and I want to design proportional control. So first thing you need to think about is to find theta, find closed loop transfer function, which is theta m over theta d. Alright, it is the closed loop transfer function is theta m over theta d. So you correct yourself later on. Theta m over theta d, that's the closed loop transfer function. And my open loop system, the plant model if you wish, is theta m over vm. That's my DC model. Okay, so then how to find my kp to satisfy some desired value? Simply what we want to do, you want to check, actually it's clear, I don't need my pen. You want to check, okay, here they call it y over r, never mind, it's output over input. Then you compare it with your desired, that's your desired transfer function, because you have a desired omega n and you have a desired z. Those are again related to your desired pole location compared to the open loop location. So you shift your open loop to a desired closed loop. So you change the pole location at the end, or we call it pole placement. So then by doing a simple comparison, we can find kp by knowing omega n. Okay, so you can find that's what we call proportional control design. Any question? You think they are easy?
No, doctor, easy.
Okay. Again here it's theta m over theta d. So theta m over theta d. But here I'm designing what PD control design. Look what they did. They take the one I explained to you in a while. They take P controller with velocity feedback or rate feedback. So they feeding the velocity. That's the position. They do the derivative. They feed back the velocity, just to avoid the effect of the zero term. That's what they did. So you can see it. Alright, then they have the open loop plant theta m over Vm, and this is the control input. So now the control input, it looks like this. So you are, that's the error, theta d minus theta m, and here minus kd s theta m. So here it's theta m, it's not theta d minus theta m. Okay, that's what proportional plus velocity feedback. Then you find the closed loop transfer function and you do the comparison. Okay, that's a closed loop transfer function, and that's your desired transfer function. Knowing omega n and zeta n, knowing omega n and zeta, you can find kp and kd. So you can find kp and kd. Yeah, you can find kp and kd. PI control design. Interesting. So here they do PI control design with reference and disturbance. So basically they add, you have the reference, but they add disturbance to the system. That's a disturbance, they apply a torque, disturbance torque applied to load of servo, to load the servo. So you are applying torque. You remember, like the lab we did in the servo motor, we apply some disturbance. And usually when you apply disturbance, you put your hand, but it's not safe, you put magnet, or maybe it could be any kind of disturbance in life, like a force applied somewhere and so on. But in your modeling, this force, uh, even in the physical system, this force will be converted through the dynamic of the system. The dynamic of your physical system will be converted to a voltage. Because here we are doing modeling, I know the dynamic of the system. If you know the DC motor modeling, how it's modeled, the electrical and mechanical part, combine them together, you know that there is a relation between the torque and velocity, between the torque and the voltage, and it's reflected by this block tau over k g equivalent, where tau is the motor time constant, k is the steady state gain of your DC motor, and J equivalent is the total inertia of your servo. So then it is a voltage at the end in physical system. So then I simulate it as if it is in physical system. I apply a torque. So here I can apply then in Newton meter. If I ask you, so you apply Newton meter, so it reflects better than you apply, okay, I apply 0.3 volt, or I apply 3 volt. So don't you can, what I asked you in your one of your assignment for the DC motor adding disturbance, you applied, basically what did you apply is not actually a torque, you applied a voltage because you injected it directly this hub. Okay, if you want to apply something that reflects a Newton meter torque, so you need to add this block in your simulation. That's it, nothing more. So here you have disturbance and you have omega d, and they want to design PD control, PI control. Okay, as we know, response to load disturbance. So if I have a load disturbance, my load disturbance is Vd. Remember from previous slide, my load disturbance is Vd. So now I take my R equals 0, as we learned, and we try to find the transfer function that related my disturbance to my output Y. Okay, so if I take this input equals 0, remember it's a linear system, I can take this 0 and then find the output, and later take this 0 and find the output, and my output actually is the summation of 2 because it's a linear system. But here I'm not interested in the reference at all. I just want to study the effect of disturbance as we did in previous sessions. So I take the zeros and the remaining system will be, I'm starting from VD, just assuming I know VD equal TD times this block. Then VD, I have this system in the forward loop, and in my loop I have minus PI, minus PI control in my feedback loop. So if that's my system, I can find y over vd or omega n over vd. Y, that's the system. Y, here is P. Okay, that's your plant P, and they call it P, and this is they call it C. If you wish, then you can find y over vd, y over vd equal P over 1 plus Pc. Forward over 1 plus loop, negative feedback, P over 1 plus Pc. Then they replace P and C by their value. P is K over tau S plus 1 and C is well Kp plus Ki over S. They get this function and they write it in the somehow general form. Okay, so S2 plus 2 zeta omega n S plus omega n square. It's not directly omega n because here as first approximation. So that's the closed loop transfer function of y over Vd. And they said, what if my Vd is a step input? What if my Vd is a step input, not unit step input, a step input with an amplitude AD? Then you replace it here, so that's your omega. Okay, they call it y in previous slide. Here they call it omega m. Doesn't matter. At the end, it's the velocity, angular velocity of the motor. So sometimes they call it y. Maybe they get confused you, but it's all right. So it helps you reflecting when reading, and checking analyzing things. So it's good to have this kind of thing. So then they said, let me take two scenarios. One, if I have only proportional controller, so I have only Kp and Ki, I'm taking it equal 0. Here I have both Kp and Ki. So if I have Ki equal 0, then this term will go out. So I'm keeping having the remaining term. And here is Ad over S. Over S, then S with S, they go out. You remaining having this one. So then, what is my steady state value? My steady state angular velocity, using the final value theorem, you will find your steady state value is that how. So then, the response to a step disturbance is not eliminated. But if you have PI controller and you apply the final value theorem, you find the response of a steady state, it's 0. So the response of a steady state guys, your response to a step input is, yes, so I'm saying in this scenario here, in the scenario 2, when you have integral control in addition to the P, the steady state angular velocity is equal to 0 in response to a step disturbance. So it means what? What's the conclusion that you draw here? Yes? What's the conclusion that you draw?
دكتور البي اي كنترول لما يكون لنا انبوت ستاب يونت يعمل elimination للستيدي ستيت ايرور.
Very nice. So right, it eliminate, but here the conclusion that you should draw that the integral controller eliminate disturbance. And I remember I was giving this note before. So eliminate disturbance. Not, I'm sure, not like eliminate what? Disturbance. Right, the integral control eliminates the steady state error, which eliminating here the steady state error with respect to a disturbance input. That means what?
Yes,
that means what? Eliminating my disturbance. So it is good to reject disturbance. So integral term, it's able to reject disturbance, which is not the case of proportional term. All right. PID control design. That's the remaining point I want to explain, and we end up here. Wednesday will be a very interesting session. Okay. If but just permit me, maybe I take 2 minutes. 2 minutes more. So that's the characteristic equation of PID controller design. That's the characteristic third order transfer function. S plus characteristic equation. Okay, so it's a third order system like this. Natural frequency, damping ratio, location of a pole. All right, it's a third order system. Cannot approximate it as second. Maybe I can approximate it as first if I wish. That's my plant model, and this is my closed loop transfer function. Alright, so this in here, this transfer function, if you remember when we explained it times ago, even maybe before the exam, I derive this formula to you. You remember, I take the whole formula in the general form when you have P and C as plant and controller, disturbance and R. We add them all together. Okay, when we cancel disturbance, we compute this, then we cancel a reference, we compute for disturbance, and we get this. Alright, your controller in this case is Kp plus Ki over S plus Kds. And your control signal, of course, equal, if that's C, U equal to, here is R minus Y. Of course, because if you have here R and here you will be having Y, so then R minus Y. Yeah, okay, that's a control input and that's your controller. Then you do closed loop transfer function. What you did, you replaced your plant. Your closed loop transfer function is this one. Okay, I'm not taking the disturbance. So PS1 plus PC. So you have P and you have C. Alright, so you replace them, you get this Y over R if you wish. Output over input. Closed loop transfer function. What we did, that's my desired characteristic equation. So as first order approximation, again, because I am not sure what do I have in the denominator, as first order approximation, I'm comparing two polynomials together, so I can 3 equation with 3 unknown Ki, Kp and Kd, and can find my Kp, Ki and Kd by knowing omega n and knowing zeta, and this P0, it's a pole that you located yourself. So recommended to locate this pole in a way doesn't affect your desired response, because everything we studied is, and the rule are applied for a second order system. So recommend, for example, to take your zeta omega n pole in here. So maybe, so then this is omega n, and this is the angle that draws zeta for you. So then, and take maybe P0 is somewhere far from, so you can neglect its effect as a designer. So then your specification will be, your response will look like a second order system. This is a recommendation. So then, as a designer, do that, because usually the specifications that you have that translate a second order system or a first order system. If a first order system, take two pole far, so you can neglect them, and then your response will be equivalent to a first order response. You do the calculation, you get Kp, Ki and Kd. Alright, and that's it. I recommend you to go over the remaining few slides. Nothing new, because you basically know them. And next time we'll start wind effect, integral wind up effect. Thank you guys. If you have no questions, if you have question, welcome.